Hello everyone. Today, Raneen, Haytham and Hanin Tass from 11A are going to speak about the Doppler effect.
In this presentation, we will be discussing 1. Christian Doppler, who discovered the Doppler effect. 2. Definition of Doppler effect, explaining Doppler effect with real-life examples. 3. Doppler effect formulas, the 4 formulas of Doppler effect. 4. Doppler effect uses, few applications of the Doppler effect.
If you're wondering where the name of this phenomenon came from, I'll make it clear for you. Christian Doppler is the scientist from the 19th century who discovered this phenomenon. He's an Austrian physicist and mathematician who is most remembered for this discovery that came to be known as the Doppler effect.
Doppler effect refers to the change in wave frequency during the relative motion between a wave source and its observer. To make it more physics-related, it is the increase or decrease in the frequency of sound, light, or other waves as the source and observer move toward or away from each other. For instance, as shown in the picture, person A hears the sound of the revving engine with a greater magnitude than person B. Person B, who's standing behind the car, receives fewer waves per second because they are spread out, which results in a low-pitched sound. But person A, who's in front of the car, receives more of those sound waves ripples per second. As a result, the frequency of the wave is higher, which means the sound has a higher pitch. Well, there is only one Doppler effect equation. This equation changes in different situations depending on the velocities of the observer or the source of the sound. And the formula is F naught equal V plus or minus V naught over V plus or minus Vs. And this stands for observed frequency equal to velocity of the sound waves plus or minus velocity of the observer over velocity of the sound wave plus or minus velocities of the source. Let us see how we can use the equation of the Doppler effect in different situations.
In situation A, the observer is at rest, so the velocity of the observer is 0. When we substitute this into the main Doppler effect equation, we get the equation of the Doppler effect when the source is moving towards an observer which is at rest. And the equation is as follows. Observed frequency equals to actual frequency multiplied by velocity of the sound waves divided by velocity of the sound waves minus velocity of the source. For example, we're having a vehicle which is considered as the source which is moving towards the observer who is at rest. Since the source is moving towards the right, each successive wave is emitted from a position closer to the observer than the previous wave. And the result from this is the wavefronts heard by the observer are closer together than they would be if the vehicle was not moving. So, the wavelength that is measured by the observer is shorter than the wavelength of the source. And if wavelength is less, frequency will be higher. This means that the frequency increases as the source moves towards the observer. Whereas in situation B, the source is moving away from the observer, which is at rest, so the velocity of the observer is 0. This means that we can eliminate initial velocity from the equation, but this time the source is moving away from the observer, so its velocity is negative, and this is to indicate the direction. So the equation becomes as follows. Observed frequency equals to actual frequency times velocity of the sound waves over velocity of the sound waves minus velocity of the source that is negative. To make it clear, I'll give an example. In this case, the car is moving away from the observer, so each wave is emitted from a position farther from the observer than the previous wave. So the arrival time between successive waves increases, which reduces the frequency. In other words, frequency decreases as the source moves away from the observer.
Situation C. Observer moving towards a stationary source. If the observer moves toward the stationary source, the observed frequency is higher than the source frequency. In this case, velocity of the source will equal to 0. Hence, we get the following equation. Observed frequency equal actual frequency times velocity of sound waves plus velocity of observer over velocity of sound wave. Situation D, observer moving away from a stationary source. If the observer is moving away from the stationary source, the observed frequency is lower than the source frequency. Since the observer is moving away, the velocity of the observer becomes negative. So instead of adding velocity of the observer, we now subtract, since velocity of the observer is negative. So the equation will be observed frequency equal actual frequency times velocity of sound waves minus velocity of observer over velocity of sound waves.
Last but not the least is the uses of Doppler effect. It has found its use in many majors, including medical field. Doctors use the Doppler ultrasound tests that reflects the sound waves to see how blood flows through blood vessels. It can show blocked or reduced flow of blood through narrow areas in the major arteries of the neck. The second use is in radar sensors. It is used in some types of radars to measure the speed of the vehicles by measuring the frequency of the returning waves. The Doppler effect is also used in astronomy, where astronomers determine how fast the stars and the galaxies are moving away from us by measuring the extent to which their light is stretched. The last use that I'll be discussing today is its use in weather forecasting. The Doppler radar measures the direction of the velocity of the objects, for example, the drops of precipitation. It is used to determine whether the movement in the atmosphere is horizontally towards or away from the radar, which aids in weather forecasting.
Thank you for listening.